This video is an introduction to chemical nomenclature, which is all about the way we name chemical substances. We already know that all of the elements have names, and this is sort of where we start with chemical nomenclature. But when we combine the elements to make compounds, the way we name things becomes a little more complicated. Nomenclature gets a bad reputation for being based on memorization and arbitrary conventions and rules that students have to learn and then will promptly forget after their study of chemistry, after their formal study of chemistry. But I'm going to argue in this video that nomenclature is actually really important for thinking about structure. Nomenclature is a bridge to structure, and the rules and conventions of nomenclature, the foundations of which we'll touch on in this video, give us insight into the structure of a chemical substance's. Names point to structure. In other words, the name of a substance, which is part of the symbolic domain, points to information on the submicroscopic domain about how atoms are connected, where electrons are located, where positive and negative charges are located, and things like this. So our learning objectives for this video are to name binary ionic compounds. We'll talk about what these are in the ensuing slides. Generating a name for those from a chemical formula is one goal, and the opposite, generating the chemical formula from the name, is also a goal here. And then we're going to do the same thing for simple molecular compounds, which consist of molecules, typically nonmetal atoms, that are bonded covalently. And here again, we want to be able to go from a chemical formula to a name, or from the name to the chemical formula in both directions. And learning the conventions of nomenclature will allow us to go in both directions. All right, let's get into it. So chemical nomenclature is a system for assigning names to chemical substances. And what a robust nomenclature system can do is allow us to go from any symbolic representation of the structure of a chemical substance to the name and vice versa. So we want to be able to go from a chemical formula or structure on one end. This is actually part of the submicroscopic level on some level, right? This is the submicroscopic domain. What types of atoms are there? How are they connected? Something like this, to a name, which is a fully symbolic textual representation of the substance. This idea in purple is really important. Nomenclature reflects the way we think about chemical structure. Names are organized and built so that we get information about structure from the name directly. This means that the rules and conventions of nomenclature are not entirely arbitrary. They are set up to automatically give us information about structure. And one of the most important general ideas that you'll see over and over and over again in chemical names is the listing of the more metallic elements first, followed by the non-metallic elements second. On a deeper level, this absolutely ubiquitous pattern relates to the distribution of charge in chemical substances. Positive charge tends to be on the more metallic atoms, and negative charge on the more nonmetallic atoms. So directly from a name like sodium chloride or potassium phosphate, for example, we get information that the positive charge is on the metal cation, sodium or potassium, and negative charge is in the second half of the name, that anionic half of the name. This even holds in the names of molecular or covalent compounds, where the more metallic elements are listed first and the less metallic elements are listed second. And so the more positively charged atoms are listed first and the more negatively charged atoms are listed second. Automatic information about structure comes from the organization of that name. In this video, we're going to focus on two general classes of compounds and the conventions for naming them. Binary ionic compounds consist of one type of cation and one type of anion, not necessarily in a one-to-one number ratio. It's just we have one type of cation and one type of anion, and the anion may be polyatomic. So the examples here are NaCl, Na plus and Cl minus. CaOH2 has Ca2 plus and OH minus ions. Still a binary ionic compound, even though we have two OH minuses in each formula unit. NH4Cl, that's NH4 plus and Cl minus, and PdNO3 2, PD2 plus and 2 NO3 minuses. These are all binary ionic compounds with one type of cation and one type of anion. And in these chemical formulas, you'll notice the cation is uniformly listed first and the anion second. We'll also talk about binary molecular or covalent compounds consisting of two types of nonmetallic elements, again, not necessarily present in a 1-to-1 number ratio. Here again, though, the more metallic element, which is further down and to the left on the periodic table, is generally listed first, and the less metallic element, generally further up and to the right on the periodic table, is listed second. Examples are NO2, CS2, P4O10, and NF3. And notice in all of these, the number ratio of the two elements is not 1-to-1. These are still binary molecular compounds, though, because they only contain two types of elements. It's worth pausing the video and checking out a periodic table to verify that the more metallic element in each case is listed first in these formulas, and the same will hold true in the name. All right, let's get into the binary ionic compounds now. Now, in order to get there, one thing we need to note is that a number of these consist of polyatomic ions, ions that contain more than one atom, where the atoms within the ion are bonded covalently, but there's a net charge overall due to, for example, a lack of electrons, in which case we'd have more protons than electrons, right? And so we'd have a net positive charge. Or we might have net negative charge if there's an excess of electrons in the ion with more electrons than protons. This table, which I won't really go through in detail, I'll just mention it, surveys the most common polyatomic ions that you'll come across. One pattern that I'll note in this table is that there's a pattern to the oxyanions in terms of the way they're named, where we start with the hypoite anion, followed by ite, ate, and perate. This same naming pattern shows up for the other halogens. Here we're looking at chlorine, but the other halogens display this exact same pattern. You'll also see this for nitrite and nitrate, where adding an oxygen to nitrite generates nitrate, as well as phosphite and phosphate, and sulfite and sulfate, where the only differences between those ite and ate ions is one additional oxygen in the ate ion. These polyatomic ions are worth either committing to memory, or if you have the luxury of having a crib sheet or cheat sheet on examinations in your introductory chemistry course, including these on your crib sheet. Most of these polyatomic ions are negatively charged. Ammonium, there in the top left, is the one exception. And so generally we'll have a monatomic cation together with an anion that's either monatomic or polyatomic. And to name binary ionic compounds, we put the name of the cation together with the name of the anion, essentially. And this slide shows the idea in general. For an ionic compound, we first want to split it up into the cation and anion using what we know about the charges of the ions. For example, if I've got a polyatomic anion in there, I can infer its charge from this table, as well as the charge of the cation. Sometimes we can get this from patterns in the charges of the monatomic cations on the periodic table. The cation may have constant charge or variable charge. There are some elements on the periodic table that can exist as cations with multiple different charges. Specifically, the D block or transition metal cations can do this. So for example, iron can be iron plus 2 or iron plus 3. And so the name needs to indicate the charge of the iron cation within the name, and we do that using a Roman numeral. So for example, in FeSO4, I can break this up into an SO4 2- anion, that's a sulfate anion, and then because the ionic compound must be neutral overall, the cation must have a charge of +2. And I have to indicate, because iron can be +2 or +3, I have to indicate in the name that the charge of the iron cation in this compound specifically is +2. Iron 3 sulfate is a completely different compound, and I do that with a Roman numeral in parentheses immediately following the name of the cation. And the name of the cation, by the way, is just the name of the element. Iron might refer to elemental iron or an iron cation. That Roman numeral also helps us see more clearly that we're referring to a cation here. In simpler cases, when the cation always has the same charge, for example, a group 2 or group 1 cation like calcium 2+, we don't need that Roman numeral since every calcium cation has a charge of +2. And again, we just name the cation as calcium, And the monatomic anions are named by taking the root of the element name, for example, chlor for chlorine, and replacing the ending with an "ide" suffix. And so this compound is calcium chloride. We don't need any indication of the number of cations or anions. This is an important thing to note with ionic compounds as well. It allows us to keep things simple. The reason we don't need an indication of the number, something like calcium dichloride or something like this, is because ionic compounds are electrically neutral, right? And so we know, for example, from the charges of the ions, the number ratio in which they must exist in the compound to maintain electrical neutrality. In binary molecular or binary covalent compounds, that's not the case. We again have two elements. We'll have the first nonmetal and the second nonmetal, but they might exist in different ratios, right, in different compounds. A simple example of this is carbon and oxygen. They can combine to form carbon monoxide, 1C and 1O in the molecule, or carbon dioxide, 1C and 2 O's in the molecule, and these are completely different compounds. The names of these compounds need to be different since the compounds themselves are different, and so we can't just say carbon oxide or carbon oxygen for the name, since that name wouldn't allow us to distinguish between CO and CO2. So we need prefixes indicating the number of each type of atom in the molecule, and these are Greek numeric prefixes like mono, di, tri, etc. This table lists them up to 10. You'll essentially never see a prefix or need a prefix requiring more than 10 atoms, requiring a reference to more than 10 atoms, since molecules just don't get that big. And when they do get that big, we have other naming conventions that you'll see if you study organic chemistry, for example. And then the second nonmetal in the formula, remember, is the more non-metallic, the more negatively charged element in the compound. Without getting into that too deeply, I'll just say here that the naming convention then for the second element is to name it like the anion, replacing the ending of the element name with "ide." So for example, in N2O, instead of just dinitrogen oxygen, oxygen becomes oxide or monoxide, since the oxygen in N2O is the more negatively charged of the two elements in the compound, and we want the "ide" suffix to point us in that direction. So this example compound here is dinitrogen, since there are two nitrogens in the structure, in the molecule, monoxide, the mon referring to one oxygen, and oxide referring to the oxygen here.